Okay, I'm going to try this again. I didn't realize that in the YouTube live panel they mirror the image for me. I guess because people are used to seeing a mirror image in themselves, so they mirror it for some reason. So I thought you guys were seeing a mirror image, but I looked at the video after and it looks like only that video has a mirror image. Now, unfortunately, this isn't ideal. I wanted to be able to, you can only see my hand or something like this or hear me talking over these notes. I was hoping that I could do it with the normal software. Unfortunately, I've been on customer support for the last half hour dealing with them. They can't seem to fix it. Hopefully, I'll be able to get it fixed by tomorrow, or if worse comes to worst, I'll be able to find a different streaming software if this software that I have been using continues to have problems. But what I'm going to do right now is I'm just going to print off the problem set 10 and the solutions that I printed off. I'm going to print those off too, so that I can just put them next to it right here. That was my original plan, and then I thought it wasn't going to work because it was mirror image. So let me just print this right now, and I will go grab a copy of this, and then hopefully I can continue to work, because it's really sucks to lose progress right now on the project. So those are just printing right now. I'm going to leave it up for the moment. I think, hold on 1 second. I think I have, yeah, I think this should be online here. So yeah, unfortunately, it's been a little bit tricky with the live streaming software, because it has been it's been causing some issues. So I'm just going to leave it open for right now. Hopefully, I'll be able to get them to fix it, but again, it might not be fixed today. Let me just go grab those there. I think the things I printed here. Thanks. All right, so we got problem set 10 over here. We have finished one and this, and I think where do we get up to? Oh, page got out of order here. So we finished. We were working, or I was working on this one here. So I'm just going to staple these all together so I don't lose track of the order of the pages. Improvising. That's what you got to do. All right. Oh, I'm out of staples here. Speaking of improvising. 1 second. Zoe, where's the stapler? I want the staples. Oh boy, all right. Here, pictures out of paper. Frustrating little obstacles here for doing projects. Unfortunately, I think in a normal setting, this wouldn't be an issue. This is just all live streaming problems. So these are not really learning problems. These are more me live streaming these problems. So here we go. We were working on meaning of the crystal momentum, and I was trying to figure out, I was trying to show this relationship here. And I wasn't able to get anything. I wasn't able to get anything from this, although it seems kind of obvious that this, change in the momentum is equal to the force. But how do we get this with this EQ? So I'm going to just cover up my notes. I'm not going to look at what I did before because I think that's going to be giving me the wrong idea. And I will try it for a little bit, and then I'll look at the solution. So we know that our group velocity is equal to this 1 over h bar. Over, so this is the derivative in Q of the energy spectrum. I can use the energy. Can I use the energy equation? Oh, can I get it stapled there? Thanks. My lovely wife helping me out in my time of need. All right. Where does this is problem 1? Okay, so these are just the solutions, so I'll just put these over here for right now. All right. So we're improvising here. These are the solutions to the old problems. I'll just put them over the side. Do I have anything that can help me here? Well, I know I need to get dHq dt. So I need to get HQ in a time derivative. If I integrate these over Q, so if I get Vg dq, then I should get Vgq is equal to 1 over, it should be EQ over H bar. So our H bar Q is equal to EQ divided by the group velocity. I mean, that should be right. So what can I do to get this into a force? Well, if I just get dHq dt, and then I get d dt on this EQ over Vg. Well, EQ should be not a function of time, I don't believe. So that should be HQ dt is equal to EQ times well, this is a function of time. This is meters per second. Am I forgetting the chain rule here? What's I'm wondering whether this is something from 803 waves. No. Hold on a sec. Just getting an update here on my technical issues here. Okay, hold on a sec. Let me just go back over here. So I'm wondering whether this Q is a... What are the units of HQ? Is Q kind of like a wave number? What is this? You know what? I'm gonna switch over and look at the solutions now. Let's see what we get here for this. Nope. All right. Yeah. All right. So looking forward here, it's saying part A. I'm just covering over part B. Work is equal to F delta X is equal to F delta X delta T How do we go from this to this one? I guess we have H bar. This was not the question I was looking at. I was thinking, how are we combining these two formulas? Oh, this is just, okay, so we're just adding it in here. So we're just going, one over H bar times H bar. This is trivially true. So we have what did they do to move this into this one? Yeah, no, I haven't semicolon, autocolon. I haven't done the human benchmark test. I don't even know what the human benchmark test is. So this is equal to VG and so if we put this is equal to VG, how are they getting that to this, to this? We have DHQ and we divide this out by VG. Oh, because this is energy, so we're equating. So we have F Vg delta T is equal to Vg delta H per Q. We get Vg's cancel. We get F is equal to H bar Q d dt. H bar is just a constant. Okay. So let's try the next question over here. Oh, I can leave this open, I guess. We're not using both cameras here. So B, let's dig deeper. If HQ is not the momentum of our electron, whose momentum is it? Suppose that this momentum is really the momentum of some particle-like object in our system, caused the quasi-particle, some effective quasi-particle mass m, and group velocity vg. Use Newton's law to show that. Okay. MA. So I'm just going to change this to a little. So this is delta x over delta t squared. This is going to be q over delta t. H bar is equal to delta x t squared. We should be able to cancel one of these. F equals MA, that is also equal to d dt bar Q. I don't know whether I can walk you through it there, Alex. I'm also dealing with the same issues that you are. So what do we have here? We have F equals ma, and we've got this dt h bar q. Well, you can ask away. I'm not promising that I'm going to have time to work on your problems on top of my own, but you can definitely put it in the chat. So we have F equals ma. Let's try to get that just 1 over a. So if we have 1 over m should be equal to a over f, and that's going to be 1 over m is equal to a is going to be this 1 over h. It's going to be dB dt and this f is dHQ dt. So let's use what we did last time to get the same idea. We're going to have some change in this velocity. What do we have here? We did this. How did we do this one? So we're going to have some effective force. Let me just flip this back. D. This is going to be the change in, that's the change in energy. And change in energy is equal to work. Force times change in X. So let's try it this way. So we have, I'm wasting a lot of paper here. So for Alex's problem, which I believe I can help with, you have to keep in mind that each photon has a specific amount of energy. So you have this total amount of energy. So you have the total energy is n times this power output. And you know from the speed of the electrons, you can get their kinetic energy. So you know how much energy the light would have had when it's coming over there. I don't know what I think you have to calculate the wavelength of the light based on the speed of the electrons coming out. And then the maximum possible photo emission rate is going to be I'm assuming that it's, yeah. So the intensity is divided by that area. So the key is to realize that the ultraviolet light has, each little photon has a certain unit of energy. Your intensity is power, so it's an amount of energy per second per square meter. You're measuring it over square meter, so you can divide out the energies, or divide out the areas. And then you just need to figure out if the photons lose the work function energy each time they kick an electron out. You can see from the remaining speed of the electrons how much energy they have remaining. So you can figure out the energy of each photon of light. And from that, you can figure it out. That's all I'm going to help with right now. I'm not going to derive it on a piece of paper. Let me go back to this problem now. How do I show that this 1 over mass is equal to 1 over h bar squared d squared dq squared eq? I'm just going to get a little water. I don't think there's any secret to it. I just keep at it. So when I get tired, I just keep working on things. I don't think you kind of just build focus over time. I don't think it's so much that I have some unusual ability to focus. I get distracted and this kind of thing. I just sort of resist the impulse to give up too early. So let's just sort of rewrite some of these things so I can see if I can get something better here. So our energy is equal to force times some change in x, which is equal to force times change in x divided by change in time. All right, and we also know that Vg is equal to 1 over h bar squared. 1 over h bar squared dEq. So we also have this equal to have F be equal to MA, which I'm going to put Vg divided by time times Vg time. So therefore, oh, there we go. 1 over mass is equal to, it was 1 over h bar, not h bar squared. 1 over mass is equal to 1 over h bar squared. There we go. So that should be right. Oops. Over here. Okay, I think this is right, although I did it a little differently. Let's go on to question 6. Group velocity and effective mass. Consider again our lattice of delta functions. Sketch VGQL and M star QL for QL less than pi in the first two bands. Where's our Q from this previous question? I think I have to look up what we did in the class. because I don't see this QL. This QL is not anywhere in these problem sets. All right, let's go through that then. U real, Q element real, not periodic. I think that's this right here. Same problem set. So what's the question again here? What happens to VG and M near the top of each band? What about in the middle of the band? So I have this from the notes here, but I don't know whether I have. Let's look back a little bit here. What is it looking for? Sketch VQL and MQL for QL. Let's find first two bands. Well, that's this, but I don't know how to derive that from what we have right now. I think that's the answer, so I'm just going to look and see if there's anything I'm missing here. taking the necessary derivatives of EQ. But what is EQ? That's the thing I'm not sure. Energy spectrum, EQ in a wave packet. So I think I'm going to probably need to do more work on this. Effective mass M is positive. Middle of the band Vg is non-zero. All right, I'm going to consider doing this question again later. So I'm just going to make a note. So let's go now to question 7. A little bit out of the frame. I'm just going to push these back a little bit here. So question 7 here. Transmission, reflection, and band gaps in 1D. Band structure is intimately connected to scattering. As we discussed in the lecture, the existence of gaps is a consequence of destructive interference between waves reflected from distant wells in the lattice. This problem will further develop the connection between scattering and band structure in 1D by using the transmission and reflection coefficients of a single isolated potential to derive the band structure of a lattice of identical such particles. Let's start by looking at a single barrier in detail. Consider an arbitrary but reasonable potential barrier described by a symmetric function Vx, which is 0 outside a region L. Simple but non-trivial way between x equals L. So this is our Vx problem from before. Okay, sending particles from the right, the energy gives this. A general energy eigenfunction, theta E with energy E, can then be expressed as a superposition of these two scattering solutions. Theta Ex is equal to, right, AB. Okay. Now we want to consider a lattice of identical such barriers. Bloch's theorem says we can find energy eigenstates which satisfy the periodicity condition. Oh, a little bit off the camera here. Periodicity condition. Theta E x plus L is equal to IQL theta E. Can this be used as visible? Yeah, I think so. A little bit smaller than my whole workspace here. Bloch then H. I remember going over this in the class. These lectures, I remember feeling like I needed to do more work on them. Meanwhile, from our study of the single well solutions above, we also know that phi e x is equal to a going from b. Side the band structures as completely determined by the transition probability and the phase shift. Which lectures did I cover this? I think this was lectures 21. Do I want to go through these lectures again before rushing through these problems? We have, I'm going to just read through what I did here to get a sense of this. All right. So we have our periodic potential. Just saying commutes with the translate by L operator. TL is equal to E BI. P at L divided by H bar. Periodic Vx. I think I'm a little too high here. Yeah. Okay. E hat TL is equal to 0. E hat P hat does not equal 0. E hat phi E. Well, if I were doing this normally right now, I think what I would do is probably just watch the lecture again and do the Feynman technique, but I didn't want to do that if I don't have it on the live stream. So I have to kind of make a decision here whether I want to. Yeah, thanks, Katya. Unfortunately, we were having technical issues with our previous live streaming software, and it wasn't working. So I might. Yeah, it's 4:30 now. I think I might even take it for today and just try to see if I can fix the live stream for tomorrow. I know I wanted to work till 6. I hate losing time here right now, but I also don't really want to start doing Feynman techniques where you guys can't see what I'm looking at. I don't know. Is there anything else I can work on in this problem set that's not to do with these? Because I feel like I don't have enough information fully understood to give these a real shot. I do have these notes here about these potentials here, but I think I need to walk through it more carefully. I did feel like this was going to be challenging when I was actually doing it. Let's see. Standing waves, the band edges. This is the last question. You know what? I think it's probably better that I go through this rather than waste time. So I'll go through this for a bit. If it looks like I'm really not able to answer any of these questions, then I might. Is there some way I can get the thing on the camera here? Let me just see if they've fixed anything here. I don't think I can do it while I'm live. Yeah, you know what? I'll just try to do it as good as I can. But even if I can't get it quite right and I have to look at the answers, and again, I'm still going to be getting some feedback. It's still better than doing nothing right now. So let's like this, like this, and I will put my notes over here. All right. What is this Bloch's theorem? I'm going to just look it up. I'll just read it out loud, and then that way I can overcome the fact that I don't have... I can't share my screen. This is very frustrating. Bloch's theorem. A Bloch wave, also called a Bloch state or Bloch function or Bloch wave function, named after the Swiss physicist Felix Bloch, is a type of wave function for a particle in a periodically repeating environment, most commonly an electron in a crystal. A wave function psi in a Bloch wave has the form psi of r is equal to e to the ikr ur, where r is the position, psi is the Bloch wave, and u is a periodic function with the same periodicity as the crystal. K is a vector of real numbers called the crystal wave vector. Okay, so we have this psi is equal to, I think we're one dimension, so I can just do x is equal to I k kx ur. This is periodic in 2 pi, 2L, sorry. Is it 2L or L? Periodic in L. Bloch waves are important because of Bloch's theorem, which states the energy eigenstates can be written as Bloch waves. Next, we prove Bloch's theorem. For electrons in a perfect crystal, there is a basis of wave function with the properties. Each of these wave functions is an energy eigenstate. Each of these wave functions is a Bloch wave, meaning that the wave function psi can be written in the form this. Defining property of the crystal is translational symmetry. A three-dimensional crystal has 3 primitive lattice vectors. Translation operator. Oh, okay. So the basic idea of this Bloch's theorem, let me go back to our notes here, is our Bloch theorem was basically this, that the translation commutes with the energy. So not really too much to that. So let's look at the show that this condition on Q and E, together with the definition of the scattering phase even above, so we have cosine of QL is going to be cosine KL minus I sine KL. I'll just squeeze it in here. E to the IX is equal to cosine minus e to the minus IX. Let me just look that up real quick. I think you just put an overall minus sign and everything, but I'm not sure. Cosine I sine X. That should be cosine negative X. Oh, so this is plus, yeah. And then this is cosine KL. Right. Cosine KL minus I sine KL. So we have where's the phi? Ooh. Oh, that's just the definition of T. So let me just write that here. T is equal to root T e to the minus I theta plus or minus I r e to the I. Okay. So we have t squared is going to be equal to t squared by 2t Well, I can just get rid of this. R squared over t. So we have, hold on a sec. I'm just gonna span it all times cosine L minus 2t cosine L plus. I think I can forget the, yeah, no, I'm gonna have to do it. So plus. Do any of these cancel? I thought they would, but maybe they don't. Let's try it. Let's try it without expanding these exponentials first and just work with this. So we have t to the minus 2I theta minus r plus or minus no restriction I guess we're squaring it, so it doesn't matter. So plus, this is just becomes an overall minus r squared minus, this can become plus. It's a 2t. Okay, 2t. So we can just factor t here. So we can just turn this into we know t and t plus r have to equal to 1. So we just have 1 over 2t of n minus 2y theta e to the ikl I'm trying to get this here. T is this. So do we get some things canceling here? So this one we just minus one of the pi, so we get cos QL is equal to e to the I AL minus this. I do 1 over 2. 1 over 2 root t, and then this is plus e to the minus I AL plus theta. So now we can exploit some trigonometry identities here. Is there a simple way I can reduce this immediately? So this should be a cosine of KL versus minus. Cancel for arbitrary theta. Am I missing a plus or minus here? No. No, this is not like this. I have to consider it. Let's do minus I. Let's factor the I out. Yep, I minus KL minus theta. So we get this, okay, minus KL minus theta. And this is minus KL minus theta. Should I not have merged those? E to the I cal minus E to the I cal. So let's just go back to this step here. So we had 1 over 2t e to the 2I theta. And then this I cal minus this should just is a cosine of KL. So that's from here. Just going to call this A. Okay. Then we get this. And then we also have no, I can't just substitute this in. This is cosine, but they're not multiple variables, so I'm making an algebraic mistake here, trying to rush this. So we do end up with e to the minus I theta over 2t just, did I make some mistakes somewhere that led to this happening? Move the time minus t off. Dr squared and r squared. I think that's probably about as far as I want to go with this right now. Let's look at what they did and see what they got. Where are we here? This is problem 6. Okay. So what they did is they started from this 2t negative I to the e I k l e minus I k l. And what do they do here? E to the minus I theta e to the k l. Oh, this is a plus k l e to the minus I theta. Okay, it's equal to. Almost had that one. But I mean, that's not bad, because if there's just some math problems, it means there's not a conceptual issue I'm missing, so I can probably keep working. Don't really need to take a break. Let's go on to question B.
For Vx, a generic potential, explain why there are no solutions to the equation derived in part A in the regions KL minus theta is equal to n pi for any integer n. These are the gaps. What role does the scattering phase play in the band structure? When KL minus phi equals n pi, cosine of n pi why are there no solutions there? I would have guessed it was pi by 2 when it equals 0. No, when it's plus or minus 1. I would have thought it was n pi by 2. What's up here? You can see? I think so. What role does the scattering phase play in the band structure? Why is this not n pi by 2? Set it 0 is 1, minus 1, 1, minus 1. Root t is equal to cosine QL. This seems fine. I don't understand what the problem is. I mean, this is a number between what is the scattering phase? This phase, I mean, it adjusts where they are. Let's see what the solution says. Since t is less than 1, right, okay. I'll write this down. Since, somebody got a little brighter there. Since t is less than 1, okay. Oh boy, I think I'm about done for today. I'm making pretty basic mistakes. So you know what? I'm going to use this to take a break. I was going to go till 6, but I think in light of the fact that we're having screen problems, let's see if I can I switch the camera on this? I don't even know that I can. Maybe I can just do this to adjust it up here. Oh, it's upside down. I'll just do this so that I can temporarily be in view. Okay. So having some issues with the live streaming software, I was not anticipating to be in this situation where I'm not able to use the software I'm using. So I'm having to just use my one camera and just YouTube Live by default. This is my normal note-taking camera. Hopefully, I will be able to figure this out either tonight or tomorrow morning for the live streaming so that I don't have to do this for a long time, because I don't like not being able to show stuff. And I've been looking stuff up online. I've been going back and forth between the lectures. And especially once I start doing the Feynman techniques, that's going to be pretty important. So I'm hoping that I can get some stuff fixed, and I will be able to resolve these issues that I was having today. I'm feeling pretty tired right now. It's been a long 3 days of studying, and I'm not as crisp as I need to be. I'm making pretty basic mistakes, like figuring out why a number greater than 1 doesn't have a inverse cosine. I'm trying to figure that out, which is obviously something that I should know. And I think it's just because I'm feeling a little bit tired. So I'm going to end it a little bit early today. We're nearing the end of the problem sets. There's a bunch more of these, but I might just go straight into doing Feynman techniques for this particular set. So I'm not sure what I'm going to do tomorrow. Hopefully, if the stream is working, I'll be able to work more in the day, but I might have to take a few more breaks just because it's been, not only with juggling work, but also keeping up with the schedule. I'm just not as crisp as I need to be right now. So I'm going to ended a little bit early today. Thank you for tolerating my my technical issues right now, and I will be back tomorrow morning, hopefully around 7. All right, take care.